and he's going to be speaking about some of the latest techniques that are being used to do forecasting of earthquakes. So it's interesting that he's speaking just before my talk, because most of the stuff he's going to be talking about is where the field is heading. The field is heading that direction. So Joe took some time last year for his senior thesis to look at the data over Japan. I think he looked at many days, many months, but particularly what he's going to show you is a 5 to 10 minutes window around the earthquake time in Japan, trying to show you whether or not they could have predicted that. Okay. So Japan happens to have a very dense network of GPS receivers, and with these GPS receivers, with the latest techniques that we're studying for earthquake forecasting, you can actually see way ahead of time the correlation between movement of tectonic plates and changes in the atmosphere. So I think you're going to find this presentation quite interesting. Are you ready? Go.
Hello. So as Dr. Corning said, I am Joe Hammerstrom. The title of my talk is Total Electron Content Correlations, Variations in Correlation with Seismic Activities over Japan. So one of the biggest advantages to doing scientific research is you can develop methods to save lives and ensure the safety of people everywhere. So you see this in your homes with like fire alarms, Geiger counters for radiation. And you can see it on a larger scale with tornadoes, hurricane warning systems, blizzards. But one natural disaster that we really haven't found a prediction method for is earthquakes. So that, fortunately, we have had work on this done by Dr. Barnaby and Dr. Hecky for 10 to 15 years now. And it's interesting that they're looking at the sky instead of the ground to find whether an earthquake is happening. So my research was a continuation of Dr. Hecky. And so let's get into that. This is a summary of my talk. I'd like to talk about the basic physics of the ionosphere and earthquakes and how they relate to GPS signals in a way that you can correlate the ionosphere with earthquakes. I'd also like to talk about what I actually did, the work with MATLAB and other tools, and also what we can do after my work to improve our correlation. So let's talk about earthquakes. You can see there's different types of earthquakes. There's a tensional stress, which is just pulling apart of the plates, compressional, pushing together, and shear stress sliding along the side. The important thing about these is they all create free charges. And these can interact with the ionosphere in a way that you can notice disturbance in the charge that was already there. So they can make the ionosphere have a higher charge or a lower charge. So we have a way to, you can see there's a connection between earthquakes and the ionosphere. The problem would be, though, how do we actually measure this charge? So let's talk about the ionosphere a little bit. It's created by ultraviolet radiation from the sun, so it's just a blanket of free charge. The main use currently is to reflect waves, and so like with an AM radio wave, you can go far away from the emitter, and you'll be able to hear it in your radio signal. But if you do that with an FM radio wave, it'll just go through the ionosphere. So the AM radio waves will bounce off. So that's off like that. An FM wave might go like that, straight through. So now we're using this idea to relate to how many charges are there. So what they're trying to look at is the TEC, the total electron content. That's literally, you take a signal, send it through the ionosphere, and it'll kind of count how much charge it encountered. And you can measure this with the phase difference between two different signals. So you'll notice here, right here, really it's a smooth curve like that. Over here, you'll have a disturbance right there, which will make it kind of fluctuate and raise up a little bit. So we know this, this total electron content can change from Earth's magnetic field and also solar activity. But now we want to relate it to earthquakes, so we can do a little research on this. So we have our theory. We want to make sure it's actually a good theory. So what we did was we looked at Japan's GeoNet data, their GPS receiver network, this massive network of over 5,000 receivers. And we looked at it on the day of the earthquake, a few days before, after, a month before, a month after, and looked at what the TEC was doing at that time. So the GPS data they collect has this TEC data. This is my actual project. This is how I did this. I received this data from Japan in this format known as Rhinex. Looks like that over here. It's a complete mess. So we need some way to actually know what we're looking at. So fortunately, Dr. Hecke sent us some code from Fortran that converts to this kind of text file, which is much nicer. You can just see that's time, that's TEC, we're good. So with that, I was able to import it to MATLAB and look at it and make sure there were no errors in the data itself, and calculate what I needed. So I changed it from just TEC over time to average TEC over space and time. As we know, the site is a stable point on Japan, so that'd be space. And then I eventually created a routine that would convert it to a video that will look at this over space, and it will be a video of 30 frames per second, and each frame is 30 seconds. So it's 900 in real time, 900 times real time. Okay, so this is an example of real data of the TEC over time. So this is some site far away from the epicenter of the earthquake, a month before the earthquake. And it's really smooth, you can see that. It just behaves smoothly and it acts normally. So that's what we'd expect on any brand new day. But on the day of the earthquake, we have data like this, which kind of fluctuates like that, which is what we're trying to look for on the day of the earthquake, because it's just the behavior we expect. So if we look at it at the day of the earthquake and we see that behavior, then we know something's up. So this is what the video will look like. It will look like that right there. They'll have a bunch of colors over space, and they'll be changing over time. Blue is low TEC, red is high, yellow somewhere in between. So we want to see if it fluctuates really fast. So I'll show you that in a few minutes. So I'll show you it now, actually. So this is the day of the earthquake I'm going to show you. The day it occurred near the epicenter, so like 100 sites around the epicenter. And watch for this 4-hour window where it fluctuates a lot. Okay. So you can see right now it's this color bar kind of shows that it's around 0. It's low. It's a fairly stable TEC over both ways. That point right there is the epicenter of the earthquake. This is the position in degrees, which is roughly distance. So watch for it, so right now it's 10 a.m. Watch for it to drop, as that will mean it's an earthquake. So here we go. So you can see it's starting to just lowering as it does over the day, over the data. And it's kind of fluctuating a little, not much, but eventually it'll just drop right about here. And that is a good indication of the earthquake. It just rapidly dropped. And it means that there's something going on. And now it's kind of fluctuating a little bit as well. So eventually it will go back up a little more. But it'll still fluctuate throughout the whole day. Not too much. But right at the time of the earthquake, you can see it's fluctuating quite a bit. Right about now, it's 4 hours after the earthquake, so it's a little harder to see now. So it goes throughout the day, goes up, still fluctuates a little, but it'll eventually just level off at 20. So that's pretty much, we already showed what happened. So the rest of the day just goes on 8 hours or so after. So let's go to the slide.
Just close.
Okay, so the way I did this research, it's fairly accurate, but there are some problems with the way it was done. We didn't have perfect data. There's bias in these files. So there'll be a little error. That's a big problem. We want to make sure there's very little error. So we have someone working on that right now, actually. We also consider the flight path of the satellite, which means it's going to be a little more error, but it's not that simple. So that's one of the first things we want to solve. But there's another problem. We want to make sure it actually is from the Earth. We don't want to have it be from something else. So here we have the atmospheric variables that we looked at. So the magnetic index changes it. To do this sunspot number, and the solar flux can also make this change. We got this data. We got data from this from the NGDC National Geophysical Data Center, and they give us these plots. So notice on the left, we want to be less than 100, less than 90, less than 4 for the solar flux, sunspot number, and magnetic index. Sunspot number is a little high, but not very high. And on the day of the earthquake, it's fine. It's 60. KP is a little high, but not enough to cause a problem. On the day of the earthquake, it's probably around 5 or 5.2. So what's interesting is the solar flux, a few days before the earthquake, it was actually 900 times 17. But on the day of the earthquake, it drops down to like 120, which is completely fine. These wouldn't cause this kind of fluctuation we're seeing in this video. But there's more work that needs to be done. This is just preliminary work. We need to remove that bias. That's probably one of the biggest things. We also want to look over more time, because it would be good to have more data to look at. It's always good to have more data. And we also want to get a method down to actually know that this is an earthquake. So it could be some solar flux causing this change, but we want to know it's actually an earthquake. So we want to develop more prediction methods to make it a quick prediction, so we can get people out of there if there's an earthquake out. For my research, I would like to thank Japan's GeoNet for providing all the data we needed and more. Dr. Hecke for doing all this work, for getting it off, and Dr. Cornely, Dr. Hammerstrom, and Dr. Free for all the help and support. Thanks.
Question for Joe? Time for 1 or 2 questions.
Can they see any type of aftershocks after the earthquakes?
I didn't look into that, but I imagine they would, just because it's the same idea. It's that pressure going across. I didn't look into that, though. Yeah.
This, going forward, if this is identified as a viable, reliable way to predict earthquakes, would there be a way to put in GPS for this that would do the job better than the existing GeoNet that's used for our navigation?
Oh, well, GeoNet is researching this kind of stuff. It looks at actual data from about a year ago. So what exactly was the question?
So is GeoNet already just for prediction of earthquakes?
It's for other stuff, but it's pretty old, so it should be good for this kind of stuff. Yeah.
Joe, I think my Western World Student University affirmed that I'm lousy when it comes to questions of physics, but if I was understanding your narration of the video, the fluctuations corresponded with the earthquake itself and with the event of the earthquake, or did they begin noticeably prior to the earthquake?
But it was mostly.
Are we talking minutes or hours, or?
You could see it a little bit, a few hours. Okay. It was mostly from the stress of the rocks, changing something in the atmosphere at the beginning of the day. So I looked into a month before. I thought I might have seen something. I can't really remember right now, but It's definitely an early warning signal.
Yeah, but you had looked far
Yeah.
back, and it's not evident until
Not
like
clear.
hours before.
Yeah.
It's still awfully good compared to just it something else.
More questions?
Does this have any crossover application to, say, volcano research? Because often, I don't know really anything about volcanoes, but my impression is that before you have something spout off, you do have some tremor similar to, that sort of masquerade as a mini earthquake.
Yeah.
So if you could apply it, if you could, to what extent, if any, would heat affect your ionosphere readings?
Heat, it might affect a little, but I'm actually not sure, but just going off something off the top of my head. But I'm not sure about that. All right, oops, one more.
Joe, thank you for a good presentation on this interesting subject, but also thank you for mentioning that wonderful, great programming language, Fortran. If you don't think it's so great, just ask the dean. He knows about it. He learned it from somebody. I don't remember who. But my real question is about the amount of coding that you did, lines of code. Were there other languages you used besides Fortran?
Well, most of my work was in MATLAB. I did a little bit of Fortran just to alter some code. And then there's some commands, but mostly it was all MATLAB.
Okay, so thanks.